Okay, so let's start, continue on the topic. So this one, I think, is just exhaustive um, listing of all the possibles. And um, basically, these are just grid. And what we can do, it's just a method of discovering the parallelogram. And altogether, 1, 2, 3, 4, 5, 6, 7, 8,
You're not
9.
sharing the screen.
Oh, sorry. Let me begin to share screen. Yes. So for this problem to be solved, at least with some sense of the accuracy, first we will trying to gauge. So this is the grid, and we going to copy a few of those grid. And so if I pick any of the grid, first we have like 4 row, 4 dot, 3 dot, and 4 dot. We have altogether we have 11 dots. And then what we can do is that the maximum 2, because we are making 2 lines basically, and the maximum arrangement of those 4 line, like, or 2 line, 2 dotted line, is actually 11 multiply 10 divided by 2. So that's going to be 55. So there are 55 different lines possible. And then those lines, some line, obviously it's not going to make parallelogram. For example, if we go to the extreme, and this line won't, because the only possible is the other lines. Then we will just trying to see that what's the lines that could possibly be making those shape. And so we can like start from the length. So one of the way is starting from the length. So basically this is a like this is a one. We can list all the possible lengths of those. So this is a 1 length, and then this is a 2 length. So 1 and a 2, and then this is a 3. Then another length, for example, this is another length. This length, this is actually 1/2. So this is 1/2 multiply square root of 3, and then is half of it. Then you multiply 2. So this length is actually square root of 3. So we can just list all the possible lengths. So this is another 2. And so this one could be like this square root of 3. So this is still possible. Basically, first, to solve this type of problem, so we can really do is that listing all the possible side lengths. For example, this one is 2 and square root of 3 if we use Pythagorean theorem. And this line going to be square root of 7. So basically, square root of 7, you still can make parallelogram. And so there are other odd shape. This one, yeah, this one is not odd. This one basically, it is a like 2. it is 2 and 1. So basically, just trying to list all the lengths of the side, then trying to seeking for it. Then I think, if you do all the lengths, then then eventually you will get it. So that's, yeah. So this is another one. For example, this is another one. So, and how to find those lengths, basically, it's also very easy. I don't think, so it actually take me a few hours to list. Eventually, I actually list all of those. So basically, to list, basically, the key to do this type of problem is find the side lengths of all the possibility. So the way to find all the side lengths is actually not too difficult. So you can just fix an extreme point. Then just because one point, you have 11 point. There's only 10 ways to make lines between other point. For example, this is a length 1. This is a length 2, length 3, length 1. This is square root of 3. And this basically, you can also you can calculate it. It's not difficult. So basically this is 2.5 and this is 2.5 on the bottom, and this side is 1/2 square root of 3. So if you calculate it, you actually will able to get this length. So basically just, then we will trying to go to the next row. And so it's very easy to exhaust all the possible lengths of those odd shape. Then you will be able to begin to list them out. And so, but after you did this problem, then you know the trick. It's not that, so this part of the math problem is that how you think. So, and so basically, the way I think after, eventually I also get those, but it's very unorganized. But then later on, when I rethink about it, how to reduce this problem more efficiently, it's just as simple. Just fix some point, exhaustively find all the possible lengths. So that will include all the odd shape and discover them very efficiently. So that's the way to do it right. So let's do this problem. And this problem actually is not a difficult one. And this one is just a very standard. So 7 unique charms are placed on bracelet. So bracelet problem is a circle arrangement. So basically, how many distinct arrangement can the charm on the bracelet are possible to arrangement are considered distinct if charms cannot show to be in the same order by rotating the bracelet or by turning it over. So basically, we need to put 7 unique charms. And the way to put the position of the first is actually 1, because it's a circular place. It's not like a line. If you arrange 7 items in a row, you have to label 1, 2, 3, 4, 5, 6, 7. And the first item will have 7 choice. And if you have a, 7 position, 1, 2, 3, 4, 5, 6, 7. If you have 7 position in a circle, the way to choose the first item looks like you have 7 tries to put the first item, but in reality, because of rotational symmetry, the first choice is only 1 because you put it here, then you begin to label the relative position of those remaining spot. So basically, the remaining spot is not labeled until the first item was put down. So that's why, it's 6 factorial. And you also remember that it's a charm. Charm basically it's a bracelet. You can wear it two direction. You can wear it upside up, or you can wear it down basically upside down, still look the same. So basically you have to divide by 2. So it's like a um, two-way of the like symmetry. So this is the way that you can view it. So anyway, um, like this is very much. I think this is a tetrahedron. Tetrahedron actually I think it actually has basically I think because it has 4 faces, so 4 faces could be put down. So basically, at least has four way of duplication. Basically, we will find out next time. I think this will be very interesting because I know that bracelet you have 2 ways to put it, still the same. So this one is actually very typical. And then so yeah, 2 circular arrangement. One is arranged table, the other is arranged bracelet or the necklace or other things. And obviously table, you cannot flip it upside down. Otherwise you are going to sit on the table as upside down. That's physically impossible unless you are in the space. And so basically that will be, 6 factorial divided by 2, 360. So this is for this problem. I think we'll do more research on this problem. Okay, so let's go to the next chapter. And next chapter basically is the probability. And so the probability actually, probability is still sounds like more like a counting, but it's not all about counting. A lot of probability is actually not counting, is above counting. So probability is study of a chance. So probability of event is based on ratio of favorable outcome to all possible outcome. And probability are between 0 and 1, or from 0% to 100%. And so probability is actually more difficult in sense that, you have to understand what you count first, because it's a lot of probability problem actually are counting problem in disguise, but it didn't tell you what to count. Counting problem at least told you what to count. So first you have to understand the terminology of the probability. So let's go through the concept of the tuple. And so first, first is the space of the probability is a very late developed branch of the math that originated from the gambling, and the pioneers are like Fermat and Pascal's um, and a lot of probability problem in the early days that it will confuse like great mind like Newton and Leibniz, who is really so brilliant that they independently invented the calculus. So probability is very difficult at that time because people haven't really grasped, they haven't invented the concept of the set. So basically, the concept of the set is really a key to solve the probability problem. And the concept of the set, so what the first concept is actually sample space. Sample space is what made up of all the possibility. So each possibility is a a equal chance end result. So we have to be very clear on what that is. And usually, if it is a limited, a finite, there are finite problems, there are pure chance problems, there are also like, geometry problem in the probability. But in the finite chance problem, which you can count, usually the end result come into a terminology called tuples. So what are tuples? So tuples usually are like ordered sequence. So finite ordered sequence. So the terminology of the tuple originate from like single, couple, double, triple, quadruple, quintuple, sextuple, septuple, octuple, and intuple. So basically, in the English or English language, so starting from triple, it's always end with PLE, and arguably couple is also from PLE, and then single is just a unique exception. So here, in the math, even empty tuple, we have a terminology called null tuple, and then we have single or monuple, couple, triple, quadruple, quintuple, sextuple, septuple, octuple, nonuple, decuple, decuple, dual decuple, tridecuple, and so it's kind of just going on. So, but normally you don't really have to remember all those names. You can just say it's n-tuple, like n-tuple. That's a accepted terminology if you don't want to remember so much things. And a tuple basically is a abstraction, is a limited like sequence. And so the first thing when you're doing the probability problem is understand the sample space. Let's starting from the basic problem of fair coin flipping. So what is the probability of flipping hand with fair coins? And everyone will know it's 1/2. But why it is 1/2? So basically the sample space is actually a two-member set. It's actually a two-tuple set. So the first tuple made up of the sample space is head. The second one is tail. So this is the whole set and made up of the sample space. So the cardinality is just a fancy word for the total count. So the cardinality of this sample space is 2. And the favorable outcome is a single member tuple set. It's a monuple made up of head only. So that's, why the probability of flipping head with fair coin is 1/2. Then let's go on to the, this is a positive integer less than 100 selected at random. So first we still have to define the sample space. The sample space basically is a monuple, which made up of like, positive integer, positive less than 100. So the first one is, the first tuple is just 1. The second is 2. And all the way to less than, so not including 100. So it's 99. So basically that is the sample space. So that's the sample space equal to this. And this is just a set notation. Then what's the favorable? That integer is odd. So the odd set, that's favorable set, basically is a tuple made up of 1 and 3 and all the way to 99. And the cardinality of this is actually equal to, so the count of this is actually equal to, 50 and over 99. So that's the probability. So this is the, then what is the probability of rolling a 6 with a pair of six-faced dice? So this one, we began to deal with more of the count. So we have a pair of dice, a pair. So a pair, so basically the sample space is a couple. So we have to understand that. So basically, if we write out the sample space explicitly, it's going to be equal to like 1 and 1. It's an ordered sequence, and a 1 and 2. Then 1 all the way to 6. Then then 2 and 1. 2 and 1 is different from 1 and 2. 1, 2, basically the first dice you roll 1, the second dice you roll 2. This is first dice roll 2, the second dice roll 1. So the sample space, the cardinality of the sample space, basically you have 36. It's just 6 to the 6 square. Then roll a 6. With roll a 6, basically you have several ways to roll a 6. You can roll 1 and 5. So is a favorite, and you can roll 2 and 4. You can roll 3 and 3, and you can roll 4 and 2. You can roll 5, 1. So basically you have 5 ways. So these are the, the favorable set is equal to this. And then in addition to doing this, you can also use a matrix. Usually if it's a 2 event, you can label the first event like this in a row. For example, this is row 1, and this is row 2. And we have 1, 2, 3, 4, 5, 6, and 1, 2, 3, 4, 5, 6. So this matrix is just help you to be organized and constructing the couple in much ordered way. So here on the intersection of row and column, we actually is 1 and 1. So that is the tuple we are constructing. And then basically, after you constructing it, you will find that this is 5 and 1. So 5 and 1 is the favorable one, and the last one is at 1 and 5 here. So basically you have this on the diagonal, you have 5 of those, and the total, so the whole thing, if you fill out this matrix, it's going to be 36. So basically it's going to be a very clear. So be clear about this. And this text box don't define this concept very clearly, but I just want you to be really understand it's the tuple you are counting, and you have to, because the probability problem really didn't it is a counting problem, but it just asked for probability directly. It didn't tell you what to count. So you have to be very explicit on what you are counting. And so this one is that all the arrangement in this word are written on a list, and one of the arrangement is selected at random. What is the probability that selected arrangement contains a double A? So double A basically is, so algebra is arrangement not containing a double A because the A and A are not adjacent. So, but what are we really counting? So the first thing we are asking is that, because this is it's asking the probability. So what we need to answer is what tuple we are trying to count. So obviously we have 1, 2, 3, 4, 5, 6, 7. We have 7 letters. So basically, if you want to be fancy, you can look up this and find the septuple or hectuple is the tuple we are trying to count to solve this problem. Or you can just say that we are trying to count the 7 tuple. I usually prefer just 7 tuple. I just hate to remember so much name to appear fancy or smart, but this serves good for me. And so the sample space is all the way to arrange those 7 letters. And how many possibilities are out there? Obviously, we have 7 letters, but we have 2A. So basically, it's actually a duplicated. So this is so right now, I just, do the probability. I'm not going to be like, because it's a 2 counting problem and 7 tuples. So all the sample space is actually 7 factorial divided by 2 factorial. So this is just 7 factorial is just how many way you can arrange algebra assume 2A are different. You can visualize it as the first A is capital A, the second A is lowercase a. So if you treat it as different, there are 7 factorial ways to arrange it. And then because the 2A are identical, so you have to discount the overcounting. The overcounting we have been doing is 2 factorial. So basically that's actually made the difference. And then what we are doing is that what is the probability that selected arrangement contains a double A? So double A, basically you will just treat it as A and A. Assume you have this letter is a single letter. Basically you reduce the letter count from 7 to 6. So basically, and double A, there's no swapping. Basically, it's just 6 factorial. So basically, that will be the all the possible way to arrange that. So what is the probability and that contains a double A? So basically, 1, 2, 3, 4, 5, 6, 7. Yeah. So basically, that's going to be 6 factorial multiply 2 factorial, because divide something equal multiply its reciprocal, then 7 factorial. So we can cancel those. Those just get 2, get 7, because factorial could be canceled. 7 factorial, you can write this 6 factorial multiply 7. So you can cancel it this way. Then you actually will get 2 out of 7. So that's the way that you can do it. And so define the end result very clearly using the tuple. Then also we can compound the events. So a lot of time it's actually easier to compound probability event. You can so the previous problem, so this some of the problem we actually these problem, some of the problem, it's actually easier to calculate if we view it differently. So let's trying to do the two red block. What's the probability of selecting two red block without replacement? And so basically we have this like four. Yeah, I didn't copy the whole problem. So we have four green block. Another trick in doing the probability problem, you really have to label it or visualize it. So four green block, even they look the same, and three red blocks, they look like the same. And when you're doing the sample space or tuple research, you cannot treat them as the same. You have to treat them as different. You have to give all the four block a different label. For example, you have to green 1 and the green 2, green 3 and the green 4. So that's the four label. Then the three red block, basically you have to use red 1, red 2, and the red 3. So those are the 7 blocks what we are talking about. Then it's asking what is the probability of selecting two red blocks without replacement. So the first question, if you do it the counting way, and then you can ask you that what is the end result of the tuple, like sample space. And basically, without replacement means that whatever you're taking out will not be put back into the selection set for the second pick. So you cannot pick two green 1. So that block will not be picked twice. So basically the sample space, it's going to be like you, and also you can view it as two ways. Sometimes, so the tuple, a lot of time it's ordered tuple. Sometimes you can also treat an unordered tuple. So unordered tuple, for example, you can actually write, for example, green 1 and the green 2. It's going to be like included with a bracelet, curly brace, and a tuple of G1 and the G2. Basically, it's ordered. It is ordered like sequence, and then it will be different from G2 and the G1. So these are just terminology trying to like make it formalized so that you can solve problems that even Newton and Leibniz got confused. So these are very important concepts, starting from very simple problem, just build a habit into using it. Then when you deal with very difficult problem, you won't confuse yourself because this is a very, concrete and accurate way to analyze problem. So what is the probability of selecting two red block without replacement? Then if we treat the whole problem as being, the end result is tuples. So basically, without any restriction, and we have 7 multiply 6 ways. Basically, is 7 permutate 2 ways to in the sample space. And then what is the probability of selecting two red block without replacement? So the way to select two red, basically you can, the first is red 1, second is red 2, then basically, you just permute it, it's going to be 3. The permuting selection space is smaller, so 3 permute 2. That's the way that you can select it. This is just from the, so basically that will be 7 multiply 6 and 3 multiply 2, and that will cancel. So basically you have 1 out of 7 ways to select those two red block without replacement. And but you actually could also view it differently. So this is just you're eyeing on the end result as the space. If you can break down the problem into a two-step problem, then each step you're using the individual like space, you will still going to get the right result. So basically you can say that to choose the first block, choosing red, the first block, just looking at choosing the first block, you are viewing the sample space as a single. The single sample space basically is, is G1 all the way to R3. So that's 7. And the way to choose one of the red is those 3 single so that's 3. So after you choosing the first one, and it could choose anyone. For example, let's visualize it choose the first red block. Then the remaining sample space has the cardinality of 6 because you have 4 green block and 2 red block left. Whatever the red is, that's 6. Then you also has 2 remaining red block. It's symmetric no matter what block you choose on the first one, it's going to be having 2. So if you view it differently, it's still going to end up with the same result, 1/7. So basically, there are a lot of probability problem. You actually have, you can view it in several different angles. So basically, this is using permutation. So this is using permutation. This is using the probability breaking to 2-step. We may be even able to use the combination. So let's try to use the combination. If we use combination, trying to choose 2 block out of 7 is actually 7 choose 2. I'm using counting, but using the combination. Then basically I am using the 3 choose 2. So choose any. So basically it's 3 choose 2 on the denominator. 3 choose 2 is equal to just 3 choose 1 is 3. And the 7 choose 2 basically is 7 multiply 6 divide by 2, and that's going to be 20.